Assalamu alaikum warahmatullah. Hello guys. Today we will talk about recurrent neural networks, chapter 10. Let's get started. I'm sharing my screen and let's play. So basically I have read this chapter 10 and it is interesting and it is also complex. And here I make some small slide which is a kind of introduction to these recurrent neural networks, and I hope you will get this grasp the idea of recurrent neural networks. So let's get started. First of all, before talking about recurrent neural networks, let's talk about what is neural networks. So neural networks are mathematical calculations inspired from biological neurons. So assume this is neuron and we have weight, we have it is bias, and we have it is activation function. When we have this X input, it goes through this neuron and it gives output of something. So how this process is happening, so that X goes inside and X get X with weight, we will have the dot product, and then we will add the bias, and the result of this we will give it to the activation function, and activation function does it work and it result as the output. So this is basic of how artificial neural networks work. So yeah, basically that. So why we need RNN? Why they are in our literature in academia? So RNN is that they saw in that time scientists had two problems. First is static input and output, which means that traditional feed-forward neural networks assume only fixed size of input and fixed size of output, which is a limitation for dynamic data. And they had second problem is lack of temporal dynamics. They process each input independently without the ability to maintain state or memory over time, which is crucial for time-dependent data. So in order to solve these things, RNN came to the playground. So RNN are a class of neural network designed specifically for processing sequential data by maintaining a memory of previous input through the internal stage updates. So it has this memory abstraction, and it has the internal loop. And recurrent neural networks are type of artificial neural networks designed specifically for processing sequential data. Unlike traditional feed-forward neural networks, RNNs have a unique feature. They operate over time. So let's look to the architecture of RNN. So RNN are a little bit complex than traditional feed-forward networks. So where we have this X input, it represents the input at each time step. This could be a feature vector in sequence, such as word in sentence, or the frame in the video, or the time point in time series data. And from X we go to the H. H is a hidden state which acts like a memory of the network. It captures information about what has been processed up to the current time step. The hidden state is crucial as it carries the information to the next time step, allowing the network to make decisions based on past inputs. And from this H, we go finally to the Y, the output of the network at each time step. Depending on the task, this could be a prediction for the next sequence element, like the next word prediction or text generation, or it can be a class label at each step or any form of processed information. So in this A array represents the transformation from the hidden state of H to the output Y. This typically involves a linear transformation followed by a non-linear activation function, such as ReLU function or etc., or softmax. the B array. This array signifies the input to the hidden state transition. The input X is processed, often linearly combined with the previous hidden state, and affects the new hidden state. And C is the most crucial part of the RNN. This arrow loops from the hidden state back to itself. This loop allows the network to carry forward information from one step to the process to the next, essentially giving the network its memory. So this is giving kind of memory sync to the network. So that is basic architecture of RNN. So let's look more deeper how this C loop is working in this hidden state. So if we unfold this architecture, this graph, we can see that the leftmost part of the diagram shows the typical cyclic structure of the RNN. The hidden state H loops back to itself, influenced by the input X at each time step. So when we unfold this cyclic dependency represents is a memory mechanism of RNN where information from previous time step is carried forward to affect future states. The unfolding process is initiated by expanding this cyclic structure into the linear sequence of operations. Each node in the unfolded sequence corresponds to the RNN operation at specific time step. Transition from left to right. This transition symbolizes breaking down the time loop into discrete steps that can be processed sequentially. So if you look here, we have nodes, and each node influences the next node. We can see the node from H from t minus 1 to the t plus 1. So each one influences the next one, and the resulting one is ht plus 1. And we can see the dotted lines. So here, so we can see the dotted lines, and which means that the structure, which means that the sequence can be beyond of this limit. So it can be more deeper or more, we can increase the number of loops here. And as you can see, when we unfold this computational graph, we can see that this is typically discrete, feed-forward, similar to feed-forward networks, which means that applying the gradient applying backpropagation will be as straightforward as applying to the feed-forward networks, going from the last to the first. So that's about the computational graph of the RNNs. Then what are the applications of RNN? So RNNs works with any sequential data because they have this memory sync, so that they can memorize the information. And second thing is that they can be very dynamic, because they can input dynamic size of input data, and they can output dynamic size of outputs. So typical applications of RNNs are speech recognition, music composition, language modeling, language machine translation, and etc. And text generation also. There are many different kind of applications of RNN. Let's talk about challenges of RNN. There is a very big challenge of RNN when we have to train them. So during the training we have 3 problems with RNN. First, vanishing gradient problem, exploding gradient problem, and difficulty in learning long-range dependencies. So during the propagation, RNNs suffer from gradients of the loss function becoming increasingly small as they propagated backward through the time step. Because of this loop, it is very often in RNNs that the gradients become very, very small, which means we will have vanishing gradient problem, or which means because of this looping process from backward to from the last hidden state to the first hidden state, during this process, we can have the gradients to be very sensitive, and they can become very, very small or very, very big, resulting in vanishing or exploiting gradient problem. And another big problem with RNNs are because of the difficulty of learning long-range dependencies. The architecture of basic RNNs inherently makes it challenging to capture dependencies between events that occur at widely separated time intervals. This limit is partially due to the vanishing gradient problem, but also because early RNN models have limited memory capacity. So, in first generation of RNNs had this problem of not the difficulty of learning the information between this long range of dependencies. But there are advanced architectures in RNNs, such as LSTM and GRU. LSTM means long short-term memory. So these two advanced architecture models are designed specifically to solve the problems with traditional RNN models. And I don't want to talk about these models currently, but just to get the idea about them is that they also belong to the RNN family, but they are specifically designed to solve the traditional RNN problems. They have some advanced computations, logics, so we will talk about in next series of videos. So to conclude, finally, what is RNN? So RNN are models designed specifically for sequential data or time series data, and they have the logic of memory, which will allow the RNNs to be dynamic, to memorize, and to understand the context or the idea through these time steps of this sequence of data. So that's it about RNNs in chapter 10. In order to understand more deeper, I highly recommend to go and check the website deeplearningbook.org, and there are many things to talk in depth actually in the book, like bidirectional. They talk more about the different architectures in RNN and about recurrency. So it will be very, very useful if you spend time and read this chapter 10. So thank you very much for your time. And see you in next series. Bye bye.